Section: Introduction. In this section, we discuss the challenges of artificial neural networks (ANNs) in retaining learned tasks, particularly the issue of catastrophic forgetting, where a network forgets a previously learned task after training on a new one. We note that many deep neural networks have excess capacity, which allows them to minimize training loss even with random labels. Our work introduces eidetic learning, a method that leverages this excess capacity to prevent forgetting. We name it eidetic learning because it aims for perfect recall, similar to eidetic memory, and it applies to all types of input data. We explain our approach, eidetic training, which involves pruning neurons after training a task until accuracy drops below a certain level. We then freeze the remaining neurons and remove connections from the pruned neurons, allowing us to reuse them for future tasks. We use structured pruning techniques to select which neurons to prune. Our method allows subsequent tasks to benefit from features learned in earlier tasks, promoting more efficient learning. Eidetic learning does not require rehearsal or replay to maintain performance on past tasks. Instead, we train a final classifier on a meta-task dataset, which includes data from all previously trained tasks. During inference, we determine the task ID from this classifier and use the corresponding classifier for the instance, all in a single pass through the network. We highlight the common practice in industry of training a deep ANN on a large dataset and then transferring its knowledge to new tasks. However, this often requires updating the ANN's parameters, which can complicate reuse and increase costs. Eidetic nets provide a solution by ensuring that learned representations are preserved while allowing for accurate performance on new tasks and minimizing operational expenses. We differentiate our approach from others that address catastrophic forgetting by focusing on preserving representation space. While some methods use a single classifier for all tasks, eidetic nets utilize a separate classifier for each task, making our approach practical and easy to implement without modifying existing architectures. We have created a PyTorch framework that simplifies the process of building an eidetic net. By subclassing our framework's class, users can easily define their network and train it on multiple tasks without needing to alter the architecture or training parameters. Eidetic nets offer several advantages. They are efficient, robust against varying tasks, stable in training, interpretable in terms of capacity usage, and maintainable by allowing for easy adjustments to network layers. Section Summary. In this section, we discuss the limitations of artificial neural networks, particularly catastrophic forgetting, and introduce eidetic learning as a solution that leverages excess capacity in ANNs to prevent this issue. Our method, implemented in eidetic nets, allows for efficient learning across multiple tasks without the need for rehearsal, ensuring that previously learned representations are preserved while minimizing operational costs. Section: Notations and Related Work. In this section, we define a neural network as a function that maps input data to output data, using a set of parameters. These parameters are organized into layers, where each layer contains a certain number of neurons. We note that the input dimensions of one layer match the number of neurons in the previous layer. We simplify our analysis by assuming a specific function that does not alter the input. We consider a scenario where we train a neural network on multiple tasks. After training on a specific task, we denote the updated parameters. We define the set of all neurons in the network and identify the smallest subset of neurons needed for each task. To prevent forgetting previous tasks, we establish two key conditions. 1. Persistence. Neurons important for a task must remain unchanged when training on new tasks. 2. Resistance. Neurons that are not important for a task should not influence the important neurons in subsequent layers after the task is trained. These conditions ensure that the network maintains its ability to perform previous tasks even as we train on new ones. If these conditions are met, we can effectively address the issue of catastrophic forgetting. We also review related work on catastrophic forgetting, which has been extensively studied. Previous research has utilized specific patterns in neural networks to improve performance on tasks like permuted MNIST. We compare our method to these approaches, highlighting that our method requires fewer hyperparameters, making it more practical for real-world applications. We explore a method that assesses the importance of neurons and maintains connections to important neurons from previous tasks to prevent forgetting. Other strategies have been proposed, including those that focus on recurrent networks and specialized layers for multitasking. Notably, we mention the sparsely gated mixture of experts layer, which allows different layers to specialize in specific tasks. Finally, we discuss approaches like nested net and Russian doll networks, which help identify efficient subnetworks within a neural network. Our method, eidetic nets, allows for more flexible reuse of features across tasks, enhancing the overall efficiency of multitask learning. Section Summary. In this section, we define a neural network structure and the conditions necessary to prevent catastrophic forgetting during continual learning, emphasizing the importance of neuron persistence and resistance across tasks. We also compare our method to existing approaches, highlighting its efficiency and integration with PyTorch, while discussing various strategies for managing neuron importance and task specialization. Section: Eidetic Learning, a principled solution to catastrophic forgetting. In this section, we outline the process for training an eidetic net on multiple tasks, ensuring that it meets the conditions for persistence and resistance to forgetting. We begin with an empty set for recording important neurons. When we train a new task, we first identify the smallest group of neurons needed to perform the previous task accurately. We then update our set of frozen neurons to include these important ones. The remaining neurons are reinitialized for the new task. To maintain resistance, we only prune connections from the recycled neurons to the important neurons of the previous task if certain conditions are met. This ensures that the important neurons remain unchanged, allowing us to train the new task without affecting the old one. Next, we describe how eidetic nets are structured within the layers of an artificial neural network, (AN). We also discuss the challenges of preventing catastrophic forgetting in self-attention layers of transformers. For the linear layer, we apply a specific operation to the input feature map, with optional bias. We train both the weight and bias parameters, using structured pruning to remove unnecessary rows. However, we must also ensure that the remaining weights do not interfere with previously pruned units. This requires us to propagate the pruning from the previous layer to the weight columns. In the convolutional layer, which functions similarly to the linear layer, we apply structured pruning to the channel dimensions. We decide which output channel filters to prune entirely and also prune the input channel filters based on the previous layer's pruning. For batch normalization, we adjust the input using 4 parameters. We compute the mean and standard deviation during training and maintain moving averages during evaluation. In eidetic nets, we freeze the learnable parameters according to the previous pruning masks. To preserve the statistics from earlier tasks, we keep the parameters in evaluation mode during new task training and prevent updates to their internal statistics. This approach ensures that batch normalization layers retain task-specific statistics, which is a significant advantage of our method. Section Summary. In this section, we outline the training procedure for eidetic nets, which involves pruning important neurons for each task to ensure persistence and resistance to catastrophic forgetting. We also describe the implementation of various layers, including linear and convolutional layers, and how batch normalization is managed to retain task-specific statistics without interference from subsequent tasks. Section: Residual Connections. In this section, we discuss the use of residual connections in deep artificial neural networks, (ANNs), to improve optimization. Our approach remains effective regardless of the specific architecture of the internal block. For instance, in a typical residual block with 2 nonlinear layers, we must carefully prune the internal components while ensuring that the residual output does not shift during subsequent task training. To maintain our guarantees, we can prune the residual connections by using the input unit mask from the first layer for the input units of the residual and the output unit mask from the second layer for the output units of the residual. This method is applicable regardless of the presence of nonlinearity or batch normalization, as long as we respect the constraints of the first and last layers. We also note that our solution can be applied to recurrent and gated models without modification. These models involve linear operations and element-wise and online arities. We simply need to ensure that the relationships between adjacent linear layers are understood, such as the connections between input hidden and hidden matrices in a vanilla RNN. As long as we respect the constraints, the use of nonlinearity will not affect the results. However, evaluating recurrent networks is beyond the scope of our current work. In our experiments, we employed structured pruning, selecting the same percentage of neurons to prune from each layer based on the lowest scores, which could be determined by either the 1 norm, 2 norm, or Taylor score. To manage time during iterative pruning, we limited the maximum training epochs for recovery and set a threshold for training set accuracy. We trained all models using the nested features outlined in our introduction. For hyperparameter selection, we held out 10% of the training set, trained on 3 tasks, and chose the hyperparameters that yielded the best average accuracy. Key hyperparameters included the pruning step size and the accuracy threshold for stopping pruning. We conducted our experiments on a single NVIDIA V100 GPU with 16 GB of memory, using the Atom optimizer without weight decay. For the permuted MNIST dataset, we followed a similar setup as previous studies, using a 2 hidden layer feed-forward network with 2,000 hidden units, a learning rate of 0.002, and a batch size of 256. Our hyperparameter grid included dropout probabilities and adjustments to the learning rate during pruning. The optimal hyperparameters we found were Taylor pruning with a step size of 5%, a stop pruning threshold of 0.1%, and a dropout probability of 0.1. We implemented early stopping during the final model training, with results indicating that accuracy remained stable across tasks. Our method's competitiveness on PMNIST is documented in our results. Lastly, we trained a deep residual network, ResNet50, on the sequential CIFAR 100 dataset across 10 tasks. In this case, we could only evaluate 1 norm and 2 norm weight magnitude pruning due to the uneven pruning behavior of Taylor pruning. We will discuss this further in the conclusion of our paper. The results from this training are presented in our findings. Section Summary. In this section, we describe our approach to implementing structured pruning in deep neural networks, including residual connections and recurrent models, ensuring that the relationships between layers are maintained. We detail our experimental setup, including hyperparameter selection and results from training on datasets like permuted MNIST and CIFAR 100, demonstrating the effectiveness of our pruning strategy. Section: High-Resolution Images. In this section, we demonstrate the scalability of our method to high-resolution images by evaluating it on images sized 224 by 224 from ImageNet, which is a subset of the ImageNet dataset. These images belong to 10 easily classifiable categories, making them likely to be accurately classified early in the training process. We assess the dataset in a sequential manner, grouping classes in pairs across 5 tasks. We trained ResNet50 using a batch size of 32 and a learning rate of 0.000125. We set the early stopping patience for pre-training at 10 epochs and did not adjust the learning rate afterward. The maximum number of recovery training epochs during iterative fine-tuning was also 10. We present the average per task accuracy across 3 runs with different random seeds in a table. We find that eidetic nets achieve strong performance for each class, even when learning the final task, despite having reduced capacity from the previous 4 tasks. Regarding the effect of the task classifier on per-class accuracy, we note that eidetic nets do not need to know the task ID during inference, which sets them apart from other methods and aligns better with real-world situations. Eidetic nets can effectively assign the task ID to new instances. To highlight the significance of this feature, we compare task routing with an eidetic net to Oracle task routing using both small and large networks. We show the evolution of per-class performance with a small MLP trained with Eidetic Learning against an Oracle task router. The results indicate that per-class performance varies when the task router has perfect test performance. Additionally, we present task routing results with ResNet 50 on CIFAR 100-5, where the average drop-in per-class accuracy is 1.8%. This indicates a performance gap that needs to be addressed through improved task routing mechanisms, especially for more complex tasks like CIFAR 10-5. While Eidetic Learning currently shows competitive performance, we see this as a promising area for future research.